Hi friends, now let us discuss what is moment area method or what is moment area theorem. So we have different methods to find slope and deflection of a particular beam. We have already discussed double integration method and Macaulay's method. This is one of the methods to find slope and deflection. Say for example, we have a beam of particular cross section and it is subjected to some UDL load and there is a concentrated load and you have some more UDL here. It is simply supported. So this beam will have a bending moment diagram. So if we roughly draw a bending moment diagram for this, let this be the bending moment diagram of this beam. So what does this method say? See, we have to find slope and deflection or displacement in y direction. So if we calculate the area and we can get slope. So say for example we have 2 points here and here. If we calculate this area, so then from this method we can get difference of slope between these 2 points and this area. Upon just finding out the area, we will be able to find slope. That is what the theorem say. Then if we, so for this area there will be a centroid point. So with respect to this line, if we find out this x bar and multiplied with this area, what is this area? Area from a bending moment diagram. So this will give us deflection. This is what the method says. So the area directly connects to the slope. So this gives one theorem, and this x bar into A, this is nothing but our first moment of area gives deflection. This forms another theorem. So we are going to discuss two theorems which connects to or one connects to slope, another one connects to the deflection. Now see this beam deflecting. So it will have an elastic curve. Because of the deflection there will be an elastic curve. This elastic curve is exaggerated. If you see this elastic curve, we can find slope. Take for example a small portion of this elastic curve. So it could be assumed as a straight line, and then this is our dy and dx. This theta, tan theta equal to dy by dx. So for a small, this is the slope, so theta will be dy by dx. Okay, so we know this already. So theta is dy by dx. Okay, so we also know for a beam ei d square y by dx square equal to bending moment. Okay, so d square y by dx square m by ei. Okay, so d by dx of dy by dx is m by ei. So this is nothing but your theta. So d theta by dx equal to m by ei. So this d theta equal to m by ei into dx. So what is this d theta? D theta is the slope between these 2 points. The difference of slope between these 2 points, or the small slope is d theta. So now if I have to get slope between 2 points, for example a point over here and a point over here, between these two, okay, so let this be C and this be D, this point, okay, D, okay, C and D. Then we have to integrate this between C, D. Now integrate here, it is because this is x distance, right, and here it is m. If we divide this bending moment diagram by ei, because it is still, the assumption is elastic, that means we are not going beyond Hooke's law. So this E is constant for a particular cross section I. If I is constant, what is this? Flexural rigidity. If we divide this, what will happen to this bending moment diagram? There is scale reduction. Some scale reduction is happening, but the curve behavior is the same. So then if we have this as our ordinate axis, see this, so CXD MEI into, for the small distance, okay, this, so this when integrated between C and D, okay, the whole area we are getting, this is Y and this is X, so we will get the area. So what we get, maybe we write this as theta D equal to, this is nothing but the difference of the theta is integral x c d m e I dx. So what is this? This is the first theorem, slope theorem. Okay, so how we can write this? dc equal to area of MEI diagram between C and D. Similarly, for any difference of slope we can obtain. So how it is difference in slope? If we draw a tangent, okay, this will be the slope for C. If I draw another tangent to x-axis, this is theta D. If we find between these two, this is our theta D, difference of theta. Okay, clear? Now let us discuss the second theorem. which relates to the displacement or the deflection. Now let us draw this elastic curve. Okay, so let us take 2 points, maybe the same point we can take. Let us take 2 points C. So this is the beam, okay, C and D. If I just extend this, okay, take the small dx, the distance between this, the small element from this reference is x1. Now if I just project these 2 points, let this be P and P dash, okay. Now if I am taking the tangent to this vertical axis, because I want the deflection, so I'm just looking at this, okay, and I'm projecting this, okay, maybe the line is not straight, nevertheless, and let this be a small what do we call as tangential deviation, a small tangential deviation, okay. So at this location anyway the tangent is going to be here. This tangent if we project, okay, this is D and this is C, let this be, this point be E. So now what is this, okay, for the small curve it is d theta. So if you take the tangent, this is nothing but d theta, okay. So this dt is equal to, because it is elastic curve, so the deformation will not be that high. So if this length is assumed to be x1, so x1 into d theta is dt. Is this clear? Okay. So now x1, what is d theta? M by ei into dx. So this is transverse tangential deviation. This is tangential deviation, small deviation. If we integrate between TC and TD, okay, x, okay, see, xd m by ei x1 dx. Okay, now this we can write as, okay, tangential deviation of C with respect to D, between C and D. So what happens, take any point on this curve between C and D, the tangent will sweep through C from C to E. So this is the the tangential deviation of C and D, okay. So we are integrating that, so we call this as TC by D, and what is this? It is nothing but our x dA integral. What is this called? First moment of area. This is equal to x bar A. Okay, so what is this T or tangential deviation between C and D? Is nothing but area of M by EI diagram between C and D into X bar, maybe precisely X1 bar. Okay, so if I'm taking the area between C and D, so this is now your C and this is D. If this is the reference, this diagram will have a centroid point. So this is X bar, X1 bar, okay, and the area is nothing but M into EI into this distance. So this is the area. So if we know the area and the location of centroid, directly we can get the deflection, the required deflection at any point. Sometimes it is different, sometimes one will go to 0, so the other one can be obtained. Okay, is this clear? So this is second theorem or moment area second theorem, which corresponds to the deflection. Okay, fine. For example, if I have to obtain a deflection at this location, then our reference point is this, and we will calculate X bar from this end. So this one will become X2. So what is that? Still the area is the same. The X bar here, instead of X1, it is X2. So at this location we will get the deflection. Is this clear? Okay, now let us explain or let us understand this with a simple problem. Okay, let us solve this problem. A cantilever beam of 3 meter length is subjected with a 50 kilonewton force, concentrated load, and there is a moment 90 kilonewton meter, and the flexural rigidity value is given as like this, and what is asked is theta B and YB. Theta B slope at B and deflection at B. Okay, so for any beam we will have bending moment. So let us take bending moment. So at this X, the bending moment, this is anti-clockwise, so it is positive 90, and this is producing a clockwise, so minus 50x. This is the expression for bending moment. Okay, so if we apply boundary condition at x equal to 0, MB will be 90 kilonewton meter. At x equal to 3 meter, MA will be 90 minus 50 into 3, so 90 minus 150, so minus 60 kilonewton meter. Okay, so now quickly we can draw the bending moment diagram. (90 kilonewton meter, 60 kilonewton meter). It's a linear variation. Okay, so at this location M equal to 0. Okay, so we have two areas, right? And this distance we have to find from similar triangle. If this is x, this is 3 minus x, so x by 3 minus x equal to 60 by 90, so 90x, So 90x equal to 180 minus 60x. So 150x equal to 180, x equal to 1.2 meter. So this is 1.2 meter. So this is 1.8. This distance 1.8 meter. Okay. This is bending moment diagram. The same diagram, if we divide by EI, okay, we can get the same diagram, right? So to get slope, difference of slope between A and B, so theta B minus theta A, we can directly take these two areas because it is between A and B. So total area we have to take. There are two areas. We have to take the two areas. We have to add it. Then we can divide with EI, or we can calculate here itself. So here 90 divided by 10, it is mega into 10 power 3 kilonewton meter square. So kilonewton meter. So this is 9 into 10 to the power minus 3 meter. Okay. Similarly, we will get here 6 into 10 to the power minus 3 meter. Okay. So we will get the same. Only scale down, that's it. Okay, so here this is 1.2, this is 1.8. Now let us find out the slope. I rub this. Slope. What is slope? Theta B minus theta A equal to areas A1 plus A2. This is A1 and this is A2. But here also, since it is below this x, what is y-axis? M by EI. Below x-axis, this is negative. Okay, so negative A1 plus A2. What is A1? This is a triangle, so half into minus half into 6 into 10 power minus 3 into 1.2 plus half into 9 into 10 to the power minus 3 into 1.8. So 4.5 into 10 to the power minus 3 radian. It is in radian. In this beam, how it will behave? Cantilever beam at x equal to 0, at A, theta A equal to 0. There is no slope. Similarly, YA will be 0. Okay. So, now we are asked to find only theta B. Since it is 0, it is only theta B. Is this fine? Now we will calculate the deflection. Okay, so deflection T A by B equal to, okay, so this is minus A1 since we want the deflection at B, this is B by A. What does it mean? The tangential deviation of B with respect to A. Okay, so into x 1 bar plus A2 x2 bar. So the x1 bar and x2 bar we have to calculate from this end. So the centroid will be here, 1/3 of this triangle, so 1/3 of 1.8, so this is 0.6 meter. Here it will be here, so from this it is 2/3, okay, 2/3 is 0.8 from here, 0.8, and this is 1.8, so from here it is 2.6 meter. So this is x2 bar, this is x1 bar. Okay, so this is minus, the area is minus 3.6 into 10 to the power minus 3. x1 is 0.6 plus this one is 8.1 into 10 to the power minus 3. This is x1. I'm sorry, this is okay, this is fine. This is x1 and this is x2 from here, because we have taken this as a1. So this is 2.6, this is 0.6. Finally we get minus 4.5 mm. What is this? Already we have set the YA is 0, so it is YB. Okay, so how it is behaving? Because at this location the tangential deviation is a straight line. Okay, so at this location this is the tangent, so this becomes your YB. For slope, if you take this slope and here the slope, there is no slope, so this becomes your theta B. Is this fine? Thank you.